This short video will review the concept of osmosis and osmotic pressure. Osmosis is a phenomenon in which a solvent will move to the solution side to lower its free energy. In this picture, what we have is a U-tube where it's a glass U-tube. On one side is pure solvent, and on the other side is solution, some solvent with, say, some sugar dissolved in it, and then a semi-permeable membrane separates the pure solvent from the solution. The semi-permeable membrane right here, it allows solvents like water, it allows solvent to pass in either direction across the membrane, but it does not allow the solute to pass. That's why it's semi-permeable. It's permeable to some molecules, but not to others. And what happens when you put a pure solvent on one side, such as water, and maybe say a solution like a sugar solution on the other side, what happens is the since the free energy of the solution will be less than the free energy of the pure solvent, the water, although it can pass in both directions, will pass more towards the solution side. And this will continue to occur with more water going towards the solution side and less water going towards the pure solvent side until the water in the solution side reaches a certain height. And once that height, it gets to be so far above the height of the pure solvent side, then the hydrostatic pressure is enough to force back, and the situation of the water going back and forth comes to equilibrium, and then the water will stop climbing on the solution side. So it's the gravity really that's pushing back, that's giving more pressure. And once it stops, then you know that the pure solvent side now has the same free energy as the solution side. So this is the concept of osmosis. Okay, osmosis. It's when when the solvent will pass towards a more concentrated solution side until it reaches equilibrium. All right, this concept then of osmotic pressure is defined as the pressure needed to stop the flow of the solvent. Okay, so if you apply an external pressure on this side, this is the solution side, this is the pure solvent side, apply enough pressure such that the water level does not increase on that side, then you force this semi-permeable membrane situation into a equilibrium situation, and the amount of pressure it takes to stop the flow of the solvent more so to the solution side is called the osmotic pressure. And the osmotic pressure is a property of the solution. That is, it's a colligative property of the solution, and it's dependent solely on the number of solute particles, not the type. And the equation for osmotic pressure, it's pi, and that's just to distinguish it from P, which is pressure. So osmotic pressure is pi equals mRT, and M is the molar concentration of the solute on the solution side. R is the gas constant, and T is the temperature, absolute temperature. It needs to be expressed in Kelvin because the gas constant is expressed in Kelvin as well. Okay, and this equation you'll need to memorize. It's kind of easy to memorize because it's a lot like the ideal gas law, which is PV equals nRT. If you divide both sides by V, then N over V is the same as molarity. So that's how I always remember this one. So you'll need to memorize this. The osmotic pressure equals the molarity times the gas constant times the temperature. Let's practice just a quick little simple problem using the equation that was originally empirically derived for osmotic pressure. What is the osmotic pressure of a 0.12 molar sucrose solution? And we'll assume it's an aqueous solution at 298 Kelvin. So it's very simple. You just pi equals the molar concentration, 0.120 moles per liter, times the gas constant, 0.08206 liter atmosphere mole Kelvin times the temperature here is 298 Kelvin. So the Kelvin unit cancels, the mole unit cancels, the liter unit cancels, and you're left, in this case, your osmotic pressure will be expressed in terms of atmosphere. And in this particular case, the value is 2.94 atmospheres. That is the osmotic pressure of that particular solution. Okay, and osmotic pressure is pretty easy to, there are devices where you can measure the osmotic pressure, and one of the main purposes for measuring osmotic pressure is to determine the molecular weight of unknown proteins and whatnot, large molecules. It's much more accurate than doing it with vapor pressure, boiling point elevation or freezing point depression.